Hi everyone, I hope that I'm audible. Let me know if you want me to raise my voice. Okay, first of all, I'm sorry that I couldn't take the lecture yesterday. I was suffering from some sort of food poisoning. Uh, we have two lectures now, which are in Kitty, and I'll schedule them sometime. So we can do one thing, I can give you an assignment, or otherwise I'll take two lectures, sometimes whenever we get time. Okay, so coming back to the scheduling, which we did in the last lecture. So we discussed about the first come, first serve scheduling. And we have seen what was the problem with this kind of scheduling. And the problem was it was bad for the processes which are input output bound. So in case there is one just a minute. So in case there is one CPU bound process which requires a lot of CPU time, it sort of blocks all the other input output processes. And if we talk about these input output bound processes, they are the ones which are the interactive processes which requires inputs from the users frequently. So it can be gaming, it can be a word processor. So anything which requires you to interact with your system frequently. So those processes are input output bound. CPU bound is one which is compute intensive process. Okay, coming to the next approach, which was already suggested by one of you in the last lecture, is if a bigger process is creating problem in this kind of first come first serve scheduling, that it is blocking the smaller processes, then why can't we go this way? Let's schedule the smaller processes first and let's keep the bigger processes for the later. So that is the idea of the second scheduling, which is the shortest job first, right? So here are queue, ready queue, you can make it based on the burst time instead of the arrival time. So you look at whichever process requires less CPU burst and you keep it at the head of the queue and schedule it. Okay, so let's do a small exercise. Can all of you compute the waiting time for this particular case which is given here? So we have four processes. You are given the burst time of every process and the arrival time of every process. Can you apply a first come first serve scheduling here and tell me what is the average waiting time? So compute waiting time for every process and just take an average. And then we'll compare what happens if we do the same thing with the shortest job first scheduling. Anyone done? You can also tell me the individual waiting times, like what's the waiting time for P0, P1, P2, P3. Those who are online can type in the chat window. Okay, Snigdha says 0, 12, 23, 26. Okay, let's do it quickly. So for P0, yes, it is 0. Right, so at the 0th instance, P0 comes, runs for 12 units. Then comes P1, hence for P1 the waiting time becomes 12, executes till 24. Then comes P2, right? So waiting time for P2 is 23, correct, because it arrived at first time unit and then it runs till 27. So the waiting time for P3 becomes 26. Good, Snigdha. Okay, so we have this. So what does average waiting time become? Take an average, 3 point, 3 point something. 23 plus 26 to the 5, 112, 61 by 4, right? So this comes out to be the average waiting time in this case. Okay, let's now try to do the same thing with the shortest job first policy. So I'm going to put the shortest job here first. So at the arrival time 0, there is only one process, which is P0. So we go ahead and schedule it. So let's say P0 runs here for 12 time units. I'll write a P0 here. It runs till 12, right? And which process will go next now? P2, right? So at 12 units, I have P1, P2 and P3 in RAM. So I'm going to look at the one which is having the least burst time and it is P2. So it's both P2 and P3. We are breaking the tie based on the process ID. So P2 goes next, runs till 15. Then you have P3, runs till 18. And then you have P1 back, runs for 12 units up to 30. Right? So what becomes the waiting time here? So P0 never waited. P1 here waited this time for 6 time units. P2 had to wait for 12 minus 1, 11, and P3 got the CPU at 15. So it waited for 15 minus 1, which is 14. And what is the average waiting time in this case? 31 by 4, right? So see how much is the difference. In the previous case, it was 61 by 4 when you do it based on Fcfs, and if you do it based on shortest job first, it's only 31 by 4. Right, so you are getting very low average waiting time in this case. Rather, if you look at shortest job first, it's optimal in the sense that there is no other way of allocating these processes so that you can reduce this waiting time. You can prove it mathematically. So you can prove it by induction. So let's say there are two processes. So definitely what will reduce the waiting time? Definitely when you put the smaller one before. So you can extend it for 3, 4, 5, so on and so forth for any number of processes. Okay, now the question is, what is the problem with this approach? So if you calculate, it will offer you lower response time, lower turnaround time, as well as lower waiting time than FCFS. Do you see a problem with this approach? So the approach is you look at all the processes which are present in RAM, and then you schedule the one which is having the least burst time. After that process is scheduled, you again look at the RAM and look at if there is any process which has the lowest CPU time, you give it the CPU, and you keep repeating it in this way. So what is the problem with this? Exactly, right? So we are always executing the small processes. So what happens to the bigger ones? So this kind of scheduling, it will always keep executing your foreground processes, which are input output intensive, which require CPU for less time, and something which requires CPU, it might actually never get executed, or it might get executed after your laptop is still open, but nothing else is really running. Okay, any other problem? So the first one is the processes which have a large CPU burst time, they are waiting. Okay, what else is the problem? So we discussed it yesterday. There is a huge problem with this. So we are working on based on the burst time of the processes, the one which requires the CPU for the least time, but we do not know that. We have no idea for how much time a process requires the CPU. So we have to predict that. So these are the few drawbacks of this. So in this case, it starves compute intensive processes, but note a difference between the two things. In the FCFS, we were saying that these are the smaller processes who are waiting for the bigger processes. And we said that we named it as convoy effect, just like how it happens in traffic when there is a bigger vehicle. And in the second case, we are calling it a starvation. So starvation is, convoy effect is when there is a bigger process, it is sitting in front of all these smaller processes, not letting them go. You are late. Next time onwards, I won't allow you. And in the second case, when we have the shortest job first, it is the opposite way. So these are all these small processes which will keep coming and occupying the CPU, and a large process has to wait. So both the situations look really the same. It looks like in the first case, these are the smaller processes which are waiting. In the later case, it looks like it is a bigger process which is waiting, but there is a very subtle difference between both of these cases. That's why we have two different terms for these. The first one is called the convoy effect. Second one is called starvation. Can you see what is the difference? So in the first one also some process is waiting, in the second also some process is waiting. So the difference here is, in the first case, if you look at these smaller processes, right, they will get executed eventually. So let's say it's a big process and it runs for 100 milliseconds. So after this big process, it is completed, these small processes, they will get the CPU because they came first. So even if let's say there is a big process which came somewhere later in your RAM, it will still wait. And these small processes, they will get the CPU because they came first. But if you look at this case, what is happening here, assume that these small processes, all of them came at 0. So their arrival time is 0. They start getting executed. Then let's say this bigger process, it came at time 2. But then let's say at time 10 came 4 new small processes, right? So this one came before, but shortest job first doesn't care about it. So shortest job first will execute these ones, and this one will keep sitting here. The bigger one will keep sitting here, right? So it might be possible that this bigger one, it does not get the CPU at all. In the first case, you will get the CPU eventually. So a very analogous case is, let's say you go shopping in a mart and then you have your trolley with you and you are at the billing counter. So the first one, convoy effect, is like if the person in front of you, he's having two big trolleys, right? So he is actually blocking you. He'll finish his task, but after that, you'll get your billing eventually. There is no one who is going to come from back in the line and get his billing done. But in the second case, starvation, it's like the person at the counter, he sees that you are having 3 trolleys and he starts billing the people who are having lesser things. So those people, they are always going to keep coming and you will wait endlessly. So in this case, the problem happens that you might have to wait endlessly. In the first one, you won't wait endlessly, although your waiting time will be increased. So that's the subtle difference between both of these. Okay, so with this, okay, just look at this Gantt chart, what we did. And can you think of a better approach here? So just logically speaking, so at time 0, we gave the CPU to P note and it executed till 12. After that, we gave the CPU to P2. Do you think we could do something else here to reduce the waiting time further? We could execute some part of P1. Yes, so that way we would reduce the response time for P1, or better even, when I was executing P0 at time 3, P2 arrived, right? So I could have actually disrupted P0 here, and at time 3, I could have actually started running P1 and P2. I could have done that, right? So that is where comes the next scheduling policy. So before starting with that, if you look at this first come first serve and shortest job first, here we followed yes, P1 waiting time in this case. Oh, I did a mistake here. Yes, it should be 18. It should be 18, right? It should be 18 here. So P1 got the CPU at 18 and it came at 0. Yes, you're correct. It should be 18. For others, it is correct. So what does it become here? 9 plus 4. It becomes 53 by 4, I guess. Yeah.
Ma'am?
Yes, yes.
Ma'am, we can't see your screen.
You can't see my screen. Uh, can you see my screen? Just try to reconnect. Oh, it's actually visible. Maybe some problem at your side.
Okay.
Okay, shall I move ahead? So if you look at both of these policies, first come first serve and shortest job first, we are following a rule here, and the rule is that whenever a process is executing, we do not interrupt it in between. We let it execute completely, and after that only we give the CPU to the next process, right? So I can say it like we are never switching from the running state back to the ready state. From running state, we are always going either to the terminated state or to the waiting state in case there is an input output required. So this kind of scheduling, it is called non-preemptive scheduling. So non-preemptive means that I'm never going to interrupt a process which is already running until and unless it is either finished or it requires an input output. And we also know that we would never use such scheduling policies in our modern day computer systems, the ones which we have. Doesn't make sense, right? Otherwise, we won't be able to execute the processes concurrently. So what we use mostly are the preemptive scheduling, where we forcefully take CPU away from the processes when required. Yes, so I think they are still in existence for the systems which have batch operating system. So where there is not a whole lot of user interaction. So something like you would use in inventories. So at the end of the day, you have to do a lot of calculations and you want everything to be stored. There you can use them because there is no user sitting who is looking forward that everything should be done quickly and he should be able to do a lot of things at once. So they are still in use, but not for general purpose computer systems. You might have some of these in supercomputers like HPCs you use, right? There, I feel like some of these might be present there. Okay. Yes, one more thing which we had to discuss is, So we said that another challenge with the shortest job first scheduling policy was we do not know what exactly is going to be the CPU burst for a process. So how are you going to predict it? So there are a number of ways to predict it, and even today people are writing research papers on it, how to predict it more efficiently. So let's get a small intuition of how you can do it. So one way of doing it is to look at similar processes. So let's say I have a process, I want to predict how much CPU time it's going to take. So uh, okay, how much CPU time it's going to take. So the two ways which you can use is look at the similar processes which might be similar in terms of size. So let's say I have a program of 2400 KB. So I know I executed such program in the past. I could take a note of how much CPU time it required. And when now I have some other process of 2400 KB, I could use that previous process to estimate it. And the second way is to use the type of the process. So whether it's a system process or it's a user process or it's a compute intensive process. So those are the two ways which we can use. Another way is to look at the history of the same process. So one way is you can again look at when I executed this process in the past, how much of CPU time it took. Right? We generally do not prefer that way because it requires again a lot of computation, and scheduler doesn't have that much time. So a CPU scheduler, it has to be very fast. Rather what we do is we look at the process while it is executing. So assuming that it's a preemptive scheduling, so let's say this process, even if it's non-preemptive, let's say this process executed from here to here, then it went for some input output, came back again, got executed for some time here, right? So these are the CPU bursts of the same process. Then it went for input output for some time, again executed for some time. So one idea is to simply take the average of all these past burst times. That will give you an idea of how much time it has to take. There can be more complicated formula which you can use. So these are some ways which people use. Okay, let's switch to the preemption now. So let's look at, yes. Yes. So rather, yesterday or day before I was looking at a paper, it came in 2015, and it actually uses machine learning to predict what is going to be the CPU burst time of a process. But yes, you have to be careful that your algorithm should be very much time efficient. Yes, so that's a big challenge there. You can use machine learning, but you have to be really, really fast. Okay, so let's switch to preemption now. So we are now going to look at the preemptive versions of both of these algorithms one by one. So the first one was the shortest job first. So now its preemptive version, it's called the shortest remaining time first. So let's take a look at how it works. It's actually also pretty straightforward. You start from time 0. At time 0, you only have P0 and P1. So start with P0, execute it till time 3. At time 3 now, I have two new processes in my RAM and one old process. So I have P1 and P2 and P3 are two new processes. Now I see P0, it requires 8 more units of CPU time. P1 requires 12, P2 requires 3, P3 requires 3. And now since P2 is the least, so I'll preempt P0, I'll send it back from the running to the ready state, and I'll start executing P2 here. So execute P2, right? P2 can go on and complete all its 3 time units here till 6. Now it is done, it doesn't require CPU anymore. Out of the remaining ones, P3 is the least. So go with P3, it executes for 3 time units. And then I have P0 and P1. So P0 is the least here, so execute P0 till 17, right? 9 plus 8. And then you can execute P1 here. Right? Where? It should be 9, right? Yes. So P note here will go to 18 and this one will be 30 here. Yes, correct. Right? How do we decide? how do we run, right? So you every time, so whenever you execute a process for one time unit, after every one time unit, just keep a track of whether there is a new process which came to RAM. So at time 0, there were only P0 and P1. So you started with P0, right? And then you saw at time 3, P2 and P3 came. So you are going to oh, yes, you're correct. I messed it up. It's a rival is one. Just give me a moment. I'll correct it. I'll correct it. Very sorry. Thanks for correcting it. So I have P note, yes, exactly, which runs from 0 to 1. And at this time, P2 and P3 come. Okay, 3 is their burst time. So you start with P2 here, run it till 4. This is the correct one. Then go to P3, which also came at 1. So execute it till 7. Now you come back to P0 and execute it for remaining 11 time units, and then you come to P1 and execute it till 30. Yes. Right. Okay. So now you could again compute the waiting time and response time in this case, and you can actually figure out it will be even better than what you got for the shortest job first. Okay. Coming to the next one. So now coming to the one which is, yes. Sorry, please. Hmm. Hmm. Yes. So if all of them came at 0, so you'll start with the one which requires the least CPU time. If there is a tie, you can select it based on whichever has the lower process ID. And yes, there will be no preemption in that case. Right? I'll never fetch CPU from some other process because no one is going to come afterwards. So I can say that in that case, response time will be equal to waiting time for most of the processes, for all the processes. Okay. Next, coming to the priority scheduling, about which we discussed on the very first day, that we should always schedule processes based on priority. Uh, so in this case, with every process, you'll have a pre-allocated priority, and it's again a preemptive algorithm. So if you are running a process and meanwhile some other process comes in RAM which has a higher priority, you are going to stop the existing process from running and execute this process which has the higher priority. So let's quickly see what will happen in this case. Let me do it here. So I do not have any arrival time given in this particular case. So we are going to assume that all the processes, they arrived at the same time, right? You have, okay, mobile. Yeah. Okay. So all the processes, they arrived at the same time, right? So let's say it's 0. So I'm going to execute the one which has the highest priority here. So this is the same case which you were referring to. So here there won't be any preemption as such because everything came at the same time, right? So it will be given to you whether a higher number means a higher priority or it is the other way. So we have seen that in Linux system, if we look at the nice values, so the lower is the value, higher is the priority. So in this case, P2 here has the highest priority. So start running P2, execute it till time 1, and then go with P5, then go with P1, then go with P3, and then go with P4, right? P4 has a burst time of 1. We have changed the scheduling policy, right? So now we are not looking at the burst time. Now we are looking at which process has a higher priority. So it can even have a very high burst time, but I'll schedule it if it has a higher priority. So actually, if you look at shortest remaining time first, it is nothing but a special case of priority scheduling where priority is defined based on your burst time. Right? So lower the burst time, higher the priority. So that's the only difference between two. You can say that is a special case of priority scheduling. So based on that, what is the problem with priority scheduling? The same problem which was there with shortest remaining time first. Not the problem of computing the burst time. Here I don't have to predict the burst time as such, but the problem of starvation. Right? So if a process it is having a low priority, then whenever a process comes which has a higher priority, it keeps running, and the processes which are lower in priority, they never get the CPU. What is the solution for this?
I mean, if they were given lower priority, doesn't it already mean that it doesn't need that much?
But sometime they should execute, right? So at some time, maybe they may go late because they are not that high in priority, but eventually they should run. But the problem is they might even not run eventually because every time in your system processes with higher priority keep coming. That's just a case it might happen.
Priority keeps getting updated.
We should do that.
Okay,
We should do
you have a
that.
process with a lower priority, there might be a priority process with a lower priority than that, which comes in later.
If two processes have the same priority, then you can choose the one with the lower process ID. So generally how we use the priority scheduling is, you actually use priority scheduling to break the tie. Like we previously said, if you are running Fcfs and two processes, they come at the same time. So then you can look at their priority and schedule the one which is having a higher priority. Right? Now here in this case, there can be some processes which are having a low priority, they might never run. So the solution is to update the priorities. Right? And how do you update the priorities? So if a process is lying there in the RAM for a very large number of time, maybe after some time you can slightly increase its priority because it has been there for a long time. So that process, that is jargonically called aging. You age the process as it is in the RAM for a long time, increase its priority after some interval, and eventually it will also get to run on CPU. Sorry, come again.
However, after some time, the previous one completes.
The
priority obviously changes. Again, we have to
Now, how will it change? See, a previous process, let's say it was having a priority of 10, right? And then that previous process completes. So that doesn't have an impact on the priority of this process. No, it's user defined or system defined. It's going to be constant.
I think what you asked is, suppose you have 10 processes and their priorities are from 1 to 10.
Okay.
So you keep running the processes 1, 2, 3. Eventually you get to 10, right?
Okay, so let me give you an example so that will make the picture clear. So let's take it like this. Let's say I am at time 0, right? And I have a few processes in RAM and I'm going to write them in an increasing order of priority. Let's say P0 has the highest priority, then I have P1, P2. Let's say its priority is 2. Let's take the same example which you are saying. I have P3, its priority is 4. I have P4, its priority is 5, right? So P node starts running here and let's say P node runs till 2 time units, then P1 runs. So it seems here that eventually P4 runs, but remember that it's a preemptive scheduling. So let's say you were running P1, right? And when P1 is running, a new process comes in the RAM, which is P5, and let's say the priority of P5 is 1. Are you getting me? So let's say P5 comes here at time unit 3, let's say. P1 was executing at 4. At time 3, a new process comes. P5, its priority is 1. Right? Which one you are going to schedule? Rather, if P5 it comes at time unit 3, you will actually stop running P1 at time 3 because the priority of P1 is 2, priority of P5 is 1. A higher priority process comes and sits in the RAM. So you'll stop executing P1 here and you will start executing P5 here. So you'll first execute P5. So if you are running a process and during that time some other process comes which is having a higher priority, you'll stop executing the current process and take that process first. So that's why the problem of starvation happens. Sorry. So aging is the solution for that. Aging is a solution for that. So this condition, it is giving rise to starvation. Let's say I have P4 which is 5. Where did it go? So P4 here is 5, right? At every time instant one or the other process comes whose priority is lesser than 5, and I keep executing that. So in this way P4 never gets the CPU, right? So aging is the solution for that. So what you can do, maybe every 10 units you can slightly decrease, or by decrease I mean decrease this value associated with each process, thereby increasing its priority. So maybe after 10 time units you can just bring P4 from 5 to 4. After another 10 units it comes to 3. So it keeps increasing its priority and eventually it will run. So that is the solution for starvation. Okay. Now, coming to the next scheduling policy, it's again very known to us. It's the first, yes. Yes, you can do that. But again, I would say that is implementation specific. It totally depends on the system programmer, how he wants to do it, right? It totally depends on you. It totally depends on the system. It's just a solution and you can implement it in any way you want. But the idea is to increase the priority. Okay. Coming to the next scheduling policy, it's also very well known to us. Actually, it is the first one which we were discussing. It's a preemptive version of first come first serve scheduling. So in the first come first serve, the only problem was if a bigger process comes and takes the CPU, smaller processes never get the CPU. So what I do, I just forcefully ask each process to leave the CPU after a fixed time interval. So I have a time quantum here. I say, okay, every process it can run for 2 units. After 2 units, it just has to leave the CPU and a new process will come. After 2 units, that new process will leave the CPU and another process will come. And I'll do this in a round robin fashion. So whichever came first definitely gets the CPU first, but it does not get to execute to its completion. It will execute for 2 time units. Then you take the one which arrived after that. That process executes for 2 time units, take the one which arrived at, and go in the same fashion. So, sorry. Yes, the amount of time each process runs is constant. So that's called a time quantum. And now it's a question, how do you decide what the time should be? Should it be 2 units? Should it be 10 units? Or should it be 20 units?
Can we vary that?
We can vary that time, but like on a whole, not between processes.
Yeah, on the whole.
On the whole, we can vary. Yes. Very sorry. On the whole, we can vary it. Right? So if you look at this diagram, the only difference between this diagram and Fcfs is here I'm going to preempt a process and I can send it back from the running state to the ready state. What can be the problems with this? So this one is not going to have a convoy effect because smaller processes will also get the CPU eventually. This one will also not have starvation because everyone else is getting the CPU also, every process. So what's the problem here?
Because here you have a big process that came in, and you have to remember what the big process did, store it somewhere. Say in the queue there's all big processes, so you have to store all the things that you've done before and keep it and then take it back again. If it's big processes, there's a lot of data you have to store to bring it back again.
Exactly, right? And you don't, we actually even, whether it's a big process or it's a small process, context switch takes time, right? So I'm going to store the content of, so what happens whenever I send a process back from the running to the ready state? I store all the data back on its process control block. I load the process control block of some other process, change the state of all the CPU registers, and that thing takes time. So it's not a very good idea to like keep on preempting processes, right? So round robin scheduling, it has a lot of context switches and hence a lot of overhead. And Context switch is totally an overhead for CPU. It does no important task as such. It's not productive at all. Right, so you have to decide, and that context switch, the number of context switches, it will actually increase if your time quantum is less. So if after every 1 unit you are preempting a process, you'll have more context switches, right? So you have to find a very nice threshold for what should be this time quantum. So if you take a very large time quantum, assume that if I take a time quantum equal to 100 milliseconds, so this round robin, it will become nothing but first come first serve itself. It will become equivalent to that, right? And then again that convoy effect will start happening. There will be a higher waiting time. And if you take this time quantum to be very less, 1 millisecond, then there is this overhead in the form of context switches, right? So you have to carefully decide what should be this time quantum here. Okay, now let's take a quick recap on all the scheduling policies which we have studied till now, and then we'll quickly discuss about two more advanced forms of scheduling policies. So we have seen a few scheduling policies. We have looked at what are their pros, what are their cons. So if you look at Fcfs, it was easy to implement, but it had a convoy effect. Input-output bound processes had to wait for a long time. So what I could say here, interactive processes here were suffering, right? And in SJF or SRTF, if assuming that we can predict the burst times quite effectively, there was a starvation, and these were the CPU bound or the background processes which were suffering. And in round robin, we had a lot of context switches. Now, can we do something that we utilize all the goodness of the different scheduling policies and come up with a new scheduling policies? So I want a scheduling policy where I take all the good things from Fcfs, so I implement it so that it's easy to implement, and then I also have something which has the features of SJF, that compute intensive processes get the CPU. They don't have to wait for a long time. So how can I do that? If I want the good features of every scheduling policies, is there a way that I can somehow run all of these together and take the good parts from everyone? So that's where comes the next scheduling policy. So this scheduling policy, it sort of groups the processes. So see, I can see that for all the processes which are compute intensive, assume that I was only having compute intensive processes in my CPU. There was no interactive process. Then Fcfs would be a good approach. I don't need to care about those interacting with the computer, and it's fine with me. Any process can execute anytime. I doesn't really care about it. So if everything was compute intensive, Fcfs would be a best choice. If everything was interactive, SJF might be a best choice, right? So what we do is we sort of classify the processes, right? So we say that, okay, I have these interactive processes here, and I have these background processes, or I have these compute intensive processes here. For all these compute intensive processes, I'm going to use first come first serve policy. And then on the other side, you have these interactive processes grouped together. You say, okay, for all these interactive processes, I'm going to use shortest remaining time first policy. Right? And then there can be some system processes which should be on priority. So as an example, assume that there are a lot of processes running on your system, and you just start hovering your mouse. It should hover, right? That is a priority, and there is a process associated with that which will enable you to see that hovering mouse, and it should have a priority, right? So that comes under system processes, or there can be some interrupt which needs to be handled very quickly. So I can have all those system processes in one group, and I can say that I am going to implement a priority scheduling on these. So I have three kinds of processes, and I'm going to use separate scheduling policies for all these kind of processes. How do I implement it? So till now, whenever I had to implement a scheduling policy, everything was in the ready queue. Based on some parameters, I would select a process from the ready queue. How do I implement this one? Come again, put them in a round robin.
Classification, we can put them in a round robin fashion. Once they're classified, you assign them to the process that they need.
Okay. So I'm going to do a round robin between these three. Is that what you are saying?
Yeah. So if you're running the System directly runs the process, right? I mean, there are three ways of running them.
There are three ways of
And we need to
running.
classify them before running them. So if we have like a block in between where classification happens, then we can just extend those particular processes to the certain.
Okay, so correct me if I'm wrong. So what you are saying is I have these three buckets with all these processes. One bucket will give me one process. It knows how to select one.
I'm saying there's a box before, like there's a tank before these three buckets, and then this tank will say to which bucket the water should fall in.
Okay, so that is for classification.
Once classified, these buckets are the ones that do the processing.
Okay, but let's say from bucket 1 I get P1 which should execute. From bucket 2 I got P2 which should execute, and from bucket 3 I got P3. So based on Fcfs I should run P3, based on SRTF I should run P2.
You send a bunch of processes, not just one. So the ones which you want to say suppose your interactive processes, the tank will send them to SRTF, the shortest time process first. You get what I'm saying?
Not really.
I'm saying, suppose you have a black box.
Okay.
That is classifying.
Okay, that is classifying. Okay.
Then what I'm saying is, once the processes are classified, you send bunch of processes into the certain queue. So you have suppose interactive processes. You send them into the batch where you do SRTF first. Then you have classified processes which are into background processes. Then you send them
Okay,
to
so I am going in a slightly different way. So just listen to me once, right? So I have these three buckets. This assume that I have classified, right? So classification is not that difficult, right? Let's say every process in this ready queue, it has a label and that tells me the classification which it falls under, right? So I have now some system processes, some interactive processes, some background processes. Now I know that on all the system processes, I'm going to use the priority scheduling. I'll select one, any of those one. So from these system processes, so let's say this system bucket says that we select this one and you should run this system process. Then from the interactive processes comes one. From our side, this one is the one which should run. Similarly, from background processes, we have one. So basically, we have three processes now, which are competing for the CPU. So which one should you run? I'll take it with you after the class. After the class, we'll discuss it, right? Okay. So what we'll do in this case, so let me come to the solution. So instead of one ready queue, let me make three queues, right? So in the first queue, I'll have all these system processes. So let's say P0 from P10, all of these are system processes, and on this particular queue, I'm going to use a priority scheduling. I have one more queue where all the interactive processes are sitting, and on this one, I am going to use SRTF scheduling. So this is priority scheduling, this is SRTF scheduling, and on this third queue where I have all the background processes, we are going to use Fcfs scheduling. Let's say first come, first serve. Now the thing is, there are three queues and hence there are three processes, but there is only one processor. So which one should I run? Right? So I define a priority between the queues. So I say that, okay, these system processes, they should be kept at the highest priority, then should come the interactive processes, and then should the background processes. So there is, inside these different queues, there can be any scheduling policy, but among the queues, there is a priority scheduling which is happening. So whenever I have to select a process, I'll first look for the system processes and choose one, if there is one in RAM. And then if there is no system processes, then I go for the interactive processes, schedule the one based on SRTF. If both of these queues are empty, then I go to background processes and run one of them. So this one is called multi-level queue scheduling, as is evident from how we implement it. Now, I'll end this and with the question that what is the problem with this? What is the problem with this scheduling? Exactly. So until and unless the queues on my top, they are not finished, you can't run the process which is there in the third queue. So again, in this starvation can happen. So if system processes, they keep coming, or interactive processes, they keep coming, a background process never gets to run. Right? And we'll discuss the solution to this in the next class. Solution is nothing but aging. aging, but you implement aging in a slightly different way here. So that's what we'll talk about. Okay, any problems with the programming assignment? Is everyone able to get started? So it's quite self-explanatory, I guess, right? You'll have to revise some of your C concepts, file handling and stuff. But if you are having a very strong starting trouble, then let me know, I'll help you. Okay.
We were accessing this one directory within the Linux system.
Yes, proc. Proc.
Direct, like proc 15.
Okay.
But like there is no proc 15.
So it might be some other ID. So try to look at what all are the directories inside proc, right? It might be so possible that there is, so that 15 actually it refers to a process ID. So every process has a subdirectory inside proc. So in that particular case, which is given in the document, 15 is actually a process. So it has a folder corresponding to it, right? So just list the directories which are there in proc and see what are the process IDs there. So it might be 8 or 9 for you, but not 15.
But then a few of the functions didn't work on them, like memory and a couple of others. And
You can get back to me, I'll help you out there, right? So we can discuss it. You can get your laptop to me sometime and we can discuss. Use any, it's okay with me. For this assignment, you can use any programming language. Okay, online students, anyone, any queries? If there are no queries, then you can leave.